Okay, we're going to take a break from writing code for a while, and we're going to talk about things a little bit more abstractly. And what I want to talk about now is the idea of deadlock. Let's get a darker shade of green here. So deadlock. So I think it's time to talk formally about deadlock. So what are the things that we need in order to have deadlock in our code? All right. Well, let's first talk big picture, what is deadlock? And then we'll talk about the things that we need. So deadlock occurs when you're using mutual exclusion to try to do synchronization in your code. So you've got multiple concurrent threads or processes running, and you're trying to coordinate them so that you don't have race conditions. But if you don't do the coordination properly, you can end up with deadlock. And what that looks like in your code typically is that your program will freeze. The threads will freeze, or a subset of threads will freeze and just stop doing anything. And that's how you know you have deadlock. So you would typically see this if you're running a program. You'd see this if you're looking at your output and all of a sudden your output freezes. And then you stop your program and you run it again and your output runs just fine for a very long time. And then it freezes again. And then you run the program again and it runs for a few seconds and it freezes. So that's usually a good indication that you have deadlock if you're using some form of synchronization and you're trying to prevent race conditions and you've got threads or concurrent executing processes that you're trying to coordinate. So what are the actual things, the ingredients that you need to get deadlock? Well, there's a couple of things that you need to have. So number one, you need to have some form of mutual exclusion or synchronization. All right. And so what that means in the context of talking about deadlock is each resource granted to only one process. Okay, so that's mutual exclusion. So you need that. This is like a checklist. Thing number two that you need, hold. So process granted resource does not release it. Okay. 3, wait. Process requesting resource will wait forever for resource to be granted. I don't have to say forever, we'll just say we'll wait for resource to be granted. If things aren't set up right and you have deadlock, it'll wait forever. 4, no preemption. A process granted resource cannot be forced to release it. And number 5, circular wait. So what this means is that you have a circular chain of processes each waiting to be granted resource held by another process in the chain. Okay. So a simple way of thinking about this of a circular wait would be if process A has some resource that it is holding and it wants a resource from process B, and process B has a resource that it's holding and it wants something from process A, then neither of those two resources are going to be granted because both processes want both resources. So you end up with a circular wait. All right, let's take a look at a sample program that can demonstrate deadlock with just a subtle change in how the program's written, okay? So we're gonna look at an example now. So let's say we have two semaphores, sem underscore t, and we'll call sem underscore t is gonna represent resource one. So this might be something like a hard drive. And then sem t might be resource two, and that might be the keyboard or something like that, okay? And so maybe both of these processes are gonna grab stuff from the keyboard and put it out onto the hard drive, all right? So here's thread A. All right, so thread A does a sem wait on resource one, and then does a sem wait on resource two. So basically, get me the hard drive, get me the keyboard, okay? Then we have some code here that says use both resources. And then we do a sem post on resource two and a sem post on resource one. Now, given that description for thread A, do we have deadlock at the moment? All right, so the criteria, number one, do we have mutual exclusion? Is each resource granted to only one process? Yes, we do. That's what the sem waits are for. When you do a sem wait, if we assume that R1 and R2 are both basically initialized to 0, or initialized to 1, then only one thread can have access to that resource. Number two, do we have hold? Process is granted to a resource and does not release it. Yes, we do have hold. If you do sem wait of R1 and sem wait of R2, you don't release it until you're done using them. Number three, do we have a wait? Will a process requesting a resource wait for the resource to be granted? Yeah, these sem waits here in thread A, definitely. When you do a sem wait, it will block until that resource is given to thread A. All right. Number four, is there no preemption? Once a process is granted a resource, it cannot be forced to release it. Yeah, we have no preemption. That's the way these semaphores work. Once a thread gets a semaphore, you can't get it back until you do a sem post. And number five, do we have a circular wait? Do we have a circular chain of processes, each waiting to be granted a resource held by another process in the chain? Or in this case, threads. Well, actually, no, we don't have a circular wait. We have a single thread, thread A. So thread A is not in a circular wait with any thread, other thread, including itself. And so we do not have circular wait. So we've met 4 out of the 5 conditions for deadlock, but we don't actually have deadlock. Let's introduce thread B. And let's assume that the code for thread B looks exactly the same as the code for thread A. So I'm just going to paste this code over here. Okay. All right. Now, do we have the potential for deadlock? Well, we certainly know that thread A and thread B meet the first four criteria for deadlock because thread B is just executing the same code as thread A. So let's think about this. Does running thread B and thread A together give us a form of circular wait? Well, let's look at the way how this could execute, right? And the way we're going to look at this is we're going to observe these two lines of code and these two lines of code and think about, is there any way if we change the order of execution of these lines of code between thread A and thread B, because there's no guarantee which is going to get executed first and whether there's a delay and which is going to get executed next. We have no guarantee other than we know that they're going to be executed in this order. So let's think about this. All right, so why don't we try this? Let's see if we can create a circular wait by having thread A do this sem wait first on R1. So if it does the sem wait on R1 first, you can write this down. So we can say A gets R1, all right? So the moment A gets R1, is it possible for B to get R1 as well? No. We have mutual exclusion here on R1. R1's a semaphore that it's 0, it's 1 or 0, and that's it. So it means you get that resource or you don't. So if A gets R1, then B is going to wait for R1. That's just what's going to happen. There's no way of getting around that. The moment A gets R1, if B starts executing, B is going to wait for R1. Okay, while B is waiting for R1, it doesn't matter how much time goes by. Eventually, A is going to get R2, and then it's going to release R2, and then A is going to release R1, and then B is going to get R1, and then B is going to get R2. And then B, like A, is going to release R1, R2, and B is going to release R1, okay, when it does the post. Okay, well, what if we switched it and we said, okay, well, what if we change things around? We have B get R1 first, all right? So the moment, because that's really, with these two lines here, that's pretty much the only order that things can happen, right? Either A is going to get R1. Well, actually, there's some other orders, so we can talk about that, but let's let B get R1 first, all right? So B gets R1. Now, is there any potential for deadlock here? Well, if B gets R1, then A is going to have to wait for R1. And that is going to let B get R2. And eventually, B is going to release R2 and R1. And then A is going to be able to get R1. And A is going to be able to get R2. And A is going to then release R2. And then A is going to release R1. Okay, let's do a final one where we just let A run, delay it for a while, and then let B run. So If we let A get both R1 and finish, eventually B will want to get R1. So this is going to work out well as well. Got the order wrong here. I release R2, sorry, that's B, release R2, and B, release R1. Okay, so basically, with the way these threads are set up, and the order that they're requesting and releasing resources, there is no potential for deadlock. We're never going to have a circular wait where A is waiting for something that B has and B is waiting for something that A has. But let's just change things just a little bit, okay? Let's change things so that the code, the order that B retrieves the resources, R1 and R2, is flipped, all right? It seems like it shouldn't matter. As long as B asks for both resources and isn't allowed to use both resources until it has both of them, it seems like the order shouldn't matter, but it turns out that it does. So what I'm going to do is I'm going to copy this. I'm going to copy this here. And we'll copy it down here. Whoops. That's interesting. Oh, I see. Okay, let's go back up here. All right. Let's grab this code. Paste it here. All right, so here's thread A and thread B. I'm going to modify thread B slightly. And what I'm going to do is I'm going to take the this up a little bit. I'm going to take the order that these sem weights are being done, and I'm going to change this so that we're not doing sem weight of R1 here and sem weight of R2. We're going to do sem weight of R2, R2, and sem weight of R1. Okay, so I just changed the order that thread B is requesting the resources. All right, so the first four conditions we know are being met automatically, but do we have the potential for circular wait here? So let's try it. So let's say thread A gets R1. So A gets R1, A gets R2, B waits for R1. A releases R2. Oh, sorry, B is going to wait for R2. Okay, so A releases R2, and that is going to allow B to get R2. A releases R1. That's going to allow B to get R1. And then B is going to release R2, and B is going to release R1. So we didn't have a deadlock in that scenario. Let's see if we can try another scenario. We'll slow things down even more. Let's say A gets R1 and B gets R2. And now A is allowed to run again, so A waits for R2 and B waits, for R1. That is going to be deadlock. Why? Well, we have a circular weight. A is waiting on R1, R2 from B, and B is waiting on R1 from A. So this is a circular weight. Okay, so that is an example of deadlock. Wow. Well, it turns out that we can actually model deadlock in a fairly effective way by thinking about A and B as if they were nodes in a graph. So let's talk about modeling deadlock. With a graph. Graphs are awesome, as Shai can attest to. Graphs are super cool. All right. So we can create a graph. Now, if you've forgotten what graphs are like, you got your nodes. So here's A, that's a node. And you've got, so I'm going to just label that, that's a node. And then you've got your edges. Whoops. Here's B, that's another node. And you've got your edge, which connects one or more nodes. So those are the nodes and the edges. So what we're going to do when we model deadlock with a graph is we're going to have two flavors of nodes. So flavor one is a process. So this is a process node. And this is a resource node. So we're going to use circle to represent a process node, and we're going to use a square to represent the resource node. All right. And then we're going to have two kinds of edges. All right. So the first kind of edge is this. A and then R. So this means A, process A, holds resource R. So process A or thread A holds resource R. So this would be like doing, in the example we're just saying, this would be like a successful SEM weight on a particular resource. If we're using the semaphore to represent ownership of a resource, that would be a successful SEM weight. Okay. The other type of edge that we're going to have is a R. So it's still an edge that connects A and R, but this means that process A is waiting for resource R. So it means that A has not acquired resource R yet. So when we go from a resource to a process, it means that we are holding that resource. When we go from a process to a resource, it means we are waiting on that resource. We don't have it yet. By the way, this type of arrow is an example of a directed graph. Okay. So what's the usefulness of that? Well, take a look at this example, this small example. So here's a process T, here's a resource T, like tape or something like that. Here's a process D. Here's a process C. And here's another resource U. Actually, you know what? I don't like that. Let's go back to what we were just doing because I think that's way better. Okay, so let's have our thread A and our thread B. So those will represent our processes or threads. All right, and we'll have two resources. So we're going to have a resource R1 and a resource R2. All right. So if in this example that we were talking about up here, A gets R1, then what that means is A gets R1. And then I think we did that. Okay, and then we said B gets R2. So B gets R2. All right. And then A is waiting on R2. So A is waiting on R2. Well, that's a graph from A to R2. So this is holds, waits, holds. And B is waiting on R1. So B is waiting on R1. And now you can see we have a graph of directed edges, and this is clearly a circular wait, right? There's a cycle here in the graph. If I start at A and I follow directed edges around from A, I end up back at A, and that means there's a cycle in the graph, and therefore I have a circular wait. So if we identify a cycle in a graph, that implies we have a circular wait. And if we've met the other criteria for deadlock, then that implies we have deadlock. All right, so I hope that makes sense. So what I want to do now is I want to work on a problem with you. Okay. So let's see, how are we going to do this problem without it becoming really tedious? Okay, I'm going to take a picture, and then I'm going to put the picture in the notes, and then we can work it out together. All right, so I'll splice it in just a second. Okay, so this is take 2 because I recorded this lecture and this part of the lecture, and apparently my computer stopped recording, so I have to do it again. Yay. All right, anyway, let's take a look at what we have here. So up at the top, we have a process or thread A, B, and C. And listed under each of these processes are the requests that the processes or threads are making for resources, and then the releases that they're doing. So process A requests R, then requests S, then releases R, then releases S. Process B requests S, then T, then releases S, then T. And process C requests T, then R, then releases T, then R. And then over here, on the far left, we have the order in which those requests are interleaved. If we assume that no two requests are executed exactly simultaneously, then the requests are going to be ordered and interleaved in some order. And so here's one particular ordering. It's not the only ordering, but it's one particular ordering. And what we want to do is we want to use a graph with directed edges to model these requests and then look to see if we end up with a cycle in the graph. All right. So we're going to start with process A requesting R, resource R. So process A would very much like to get resource R, And it turns out that all the resources are free right now. So process A does in fact get resource R. So we're going to draw a directed edge from R to A. So that's step one, check. Now B requests S. So we got to set up A having R, and B is going to get S, no problem. All right, and now we have that's step two. And then step three, C requests T. Well, A has R, B has S, C now has T. No problem. That resource was free for T to grab. Okay. The next thing that's going to happen is A is going to request S. So we're going to first set up the state before A requests S, and then take a look at this. So A is requesting S, but the problem is B already has S. So we have to draw a directed edge from A to S, indicating that A is holding, or A is waiting for S. It's holding R, but it's waiting for S. B requests T. So let's just draw the state of everything before B, the request for T from B is processed. So B requests T. Well, C already has T, so B is going to wait for T. All right, and then we're just going to draw the state of the graph before we do the last instruction here. So the last instruction is that C requests R. So R is already being held by A, so C is going to have a directed edge from C to R, showing that it would like R, but it doesn't have it. And so now the question is, do we have a cycle in the graph? So if I draw this red and start at A, if I start at A, do I end up back up at A if I follow some of the directed edges in the graph? Well, here I am following the directed edges. Yep, and it looks like I end up back at A. So we do have a cycle, and that means that we have deadlock. Okay, cool. So that's a demonstration of how you can use the graph to detect deadlock. Now, what we'd like to do is do the same thing, but maybe take a look at this in a different order. Take a look at the requests in a different order. For a slightly different scenario, and I've rewritten the order. So over here on the left, what we see is that A is going to request R first, and then C is going to request T, and then A is going to request S. So it's a slightly different order, and so what I want to do is I want to graph what this looks like. The thing to note, though, is that both A, B, and C all are requesting and releasing resources in the same original order. It's just that the interleaving of the requests is different, right? And let's see what happens. Okay, A requests R, and it's going to get that R because no one is interested in R at the moment. And then we have C requesting T. Okay, C is going to get T because no one's interested in that at the moment. Now, A is also requesting S. Okay, so A requests S. So we've taken care of that, that, and that. Now C is going to request R. So that's the fourth scenario. So this is 3, 4. Okay, so let's just draw what things look like before C requests R. Now, C requesting R is going to be a bit of a problem because R is being used by A right now. So we're going to draw a directed edge from C to R, indicating that C is waiting for R. Now, at this point, do we have a cycle? Let's see if we can try to trace it. Let's start at, well, if we start at A, we're not going to go anywhere. If we start at B, we're not going to go anywhere. Let's start at C. So if we start at C, we're going to go down here. and we're going to go to R, and then we're going to go to A, but then we're going to stop. We can't go anywhere once we leave A. So let's do that again. So it looks like we don't have a cycle in the graph. And so we can continue. A releases R. So now when A releases R, it looks like this. And as soon as A releases R, that means that C is actually going to get R because it was waiting on R. All right. And then A releases R, and then A releases S. So when we're done with this, we have C owning T and R, and A's finished. And we don't have any deadlock. And now that C owns T and R, C can also run to completion and release T and R when it's done. So that's a scenario where there's no deadlock. So depending on which interleaving you have, you can either have deadlock or not. Okay. So this was somewhat complicated, but identifying the cycle in this graph wasn't too complicated. I mean, you could kind of look at it and see that there is a cycle. But it might be really interesting to attempt to look at a more complicated graph and think about between resources and processes, could we identify a cycle in the graph? And so to do that, what I have is I have a state of the graph. And what I'd like you to do is I'd like you to read through these 7 states, starting with process A and ending with process G. And what I'd like you to do is draw your own directed graph that maps out this situation 1 through 7. So process A holds R and waits for S. Process B holds nothing. This means nothing. So you're not going to draw process B holding a particular resource and waits for T. Process C is holding nothing again and waits for S. Process D holds U and waits for S and T. Process E holds T and waits for V. Process F holds W and waits for S. And process G holds V and waits for U. So what I want you to do right now is draw the directed graph that shows this and see if you can find any information in the directed graph to indicate whether we're in a deadlock state or not. Okay, so let's see if we can draw this graph. So we start out with process A. Process A holds R and waits for S. Maybe what I could do is I like to be able to see this at the same time that I'm drawing it. So what we'll do is see if we can shrink this. That's so cool. All right. And we'll put it up over here in the corner. It's rotated slightly, so let's see if we can get that. Okay, perfect. All right, so process A holds R and waits for S. So here is R, and process A is going to hold R and wait for S. So we're going to draw a directed edge between A and R. Process B holds nothing and waits for T. All right, so we have process B. Process A is also waiting for S. We're going to draw an arrow between A and S. All right, so process B holds nothing, but it's waiting for T, process T. Okay. Process C holds nothing and waits for S. Okay. Process D holds U and waits for S and T. Well, I'm going to just see if I can make a little bit of space here, because then I can fit that process D right here. So process D holds U and it waits for S and T. So D holds U, but it's also waiting for S and T. Okay, so I've taken care of these three. Now process E holds T and waits for V. So E holds T and it's waiting for V. Process F holds W and waits for S. So here's F, oops. So here's F, and it holds W. And it's waiting for S. Okay. And finally, we have process G, which holds V. So it's got V, but it's waiting for U. All right. So maybe your graph looks as neat as mine, but I would say that I have a slight advantage because I've done this graph before, so I kind of know what it's going to look like. And how this is drawn looks kind of neat, and when you look at it, you can definitely see that there is evidence here of a cycle, right? If we start at D and we follow D along these directed edges, we end up back at D again. So we definitely have a cycle in the graph. So that means that we have deadlock. Now, as you can imagine, working with this, if you have a lot of processes and you have a lot of resources, you're going to end up in a situation where it may be very difficult graphing the processes and resources and the directed edges in a way that reveals the cycle. So it probably makes sense to use an algorithm to detect the cycle rather than eyeballing it. And so that's what we're going to do next. So if we're going to look for a cycle in the graph, there's a lot of cycle detection algorithms that are out there. So I'm going to give you one that's fairly straightforward, I think. Step 1, get a list of all nodes. So we're getting a list of all the nodes in the graph. We're just going to put them in a big list. So in this case, the list is R, A, B, C, S, D, T, E, F, G, U, V, W. The order of this doesn't matter. I just went from left to right, basically. Okay, so that's step 1. Let me make sure I have them all. R, A, B, C, S, D, T, E, F, G, U, V, W. Okay, that's step 1. And then pretty much for each step 2, for each node in the list, we're going to do the following. So we're going to start out with node R. we're going to create another list that is a list of the nodes that are visitable or reachable from R. Now, when you have a directed graph like this, just because two nodes are connected doesn't mean that they're reachable. It just depends on what direction the directed edge goes. So if we start out with R, since that's the first node in the list, what nodes are reachable from R? Well, if we go from R to A, that's reachable. So we're going to list R and A. All right. Now, as we move from R to A, we're going to mark that edge as an edge that we've explored already. So we don't want to explore that edge. We don't want to go backwards and go from R to A again, because that would put R in again or A in again. We don't want to do that. We only want to visit a node from a particular edge one time. All right, so from R to A, and then we can go from A to S. All right, so we're going to add S there. Now, if there's nothing left to visit, in other words, we're now at S, right? Can we go anywhere from S? No, because all of the nodes that reach S have directed edges going into S, and there's nothing going out of S, so we're pretty much stuck. So we're done exploring that first node in the list, the node R. Now what we're looking for is duplicates. If we see a node appear more than once in this list that we're constructing, then it means that the graph has a cycle in it. Okay, so let's now go to A. All right, so we'll reset our directed edges here. Oops. And we're going to say, if we're at A, what nodes can we reach from A? Well, if we start at A, the only node that we can reach from A is S. So we're going to mark that edge as an edge that we've visited through, and we're going to write A and S. And that's pretty much, when we're at S, all nodes are leading into S and not out of S, so we're pretty much done with the exploration of all the nodes that are reachable from A. All right, so that's taking care of A. Let's do B. So B is a little bit more interesting. All right, so from B, we can, let me just go back and clean that up. Clean this up. Okay, so from B, we can reach the node T. And from T, we can reach the node E. From E, we can reach the node V. From V, we can reach the node G. Boy, this is quite interesting. From G, we can reach the node U. And from U, we can reach the node D. Now, when we're at D, we can go to two nodes, S or T. We just have to pick one that we're going to follow. So I'm going to go left. I'm going to visit the node T. I'm sorry, I'm going to go left. I'm going to visit the node S. So from D, we can go to S. And when we're at S, it doesn't look like we can go anywhere else, right? Because again, all nodes are leading into S. There's no directed edges that are going out of S. So we'll go back to D again and say, where else can we go from D? Oh, there's another unmarked edge that's leaving D that goes to T. So we'll write T down. And now, one of the things I should be doing each time I put a node into the list is asking the question, is that node a duplicate? All right, and when I put T down here, because it already exists in the list and we have a duplicate, that means, aha, we have a cycle. Because if you start at node T and you visit all of the nodes that T can visit, and you follow that all the way around and you end up back at T, it means that there's a cycle in the graph. And if we have a cycle, it means that we have deadlock. Okay, so that is an algorithm for detecting a cycle, and that's something that we can use if we want to determine if a set of nodes and resources and the resources that the nodes have or hold and the resources that the nodes are waiting on sets up a cycle in the graph and sets up deadlock. Included here in the class notes a copy of a more formal description of the algorithm. But if you understand the visual version that we just went through, then you're going to completely understand the text for this formal algorithm. And it's in the notes. You don't have to write it down. You can just go to the class notes that are online for this. All right.